And we're live.
All
Hello,
right.
everyone.
Hello, everyone, and welcome to our June uh, PyData Montreal meetup. So today we have a somewhat unusual event because we only have one main guest, and that's Itamar Turner-Trauring. He's the author of pythonspeed.com. It's a website. It's an excellent website where Itamar writes about Python, writing, kind of speeding up your code, dealing with big data sets, and how to package your uh, Python projects in Docker using best practices. So today we have two talks by Itamar. The first one will start in a few minutes on small big data. So how to use NumPy and Pandas when your data doesn't fit in memory. And right after that, we'll have a talk on Docker packaging. So with that said, Itamar, the stage is yours. So feel free to go ahead and share your slides.
Sure. And should we just have a short intro if the time is to start at 6:10?
No, I think we can start with your you can start with your introduction and then go into the first presentation.
Okay, so let me share the window. Okay, so you should see this now.
Yes.
Okay. Here's full screen. Just to introduce myself, my name is Itamar. As Alex said, I write on pythonspeed.com. And the two topics I'm going to be talking about today are pretty different. But the general theme is that software is this really amazing tool. And you, as people who use software, can build amazing things with it. But there are a whole bunch of technical details and tools that, while useful, can get in your way if you don't understand them. And so my general goal is to help you get better at doing whatever it is your goal is. So like your personal goal, your business goal, your organizational goal, by teaching you sort of additional skills and sort of empowering you to do more with your software and your computer. And I spend a lot of time writing. I do some consulting. I have some products. I do some training. But in general, the big picture idea is that, particularly with Python, but more broadly, I want you to be able to do more than you could do by using the tools or techniques I'm going to teach you. And the first talk is about small big data, which I'll define in a bit, and what to do when your data doesn't fit in memory. So before I get into the details, like whenever you're writing software, the first thing you should be doing is asking yourself whether the software should be written at all. Because if you're writing code that hurts people, hurts the environment, then the more effective you are, the better you are at your job, the more damage you're causing. And so insofar as my hope is that you will be more effective by learning those techniques, like the better you are at what you do, the more important it is to ask, should you be doing this in the first place? So before you start any project, please make sure to think about whether it's a project that should be written, whether it's software that will actually not cause damage to others. So with that aside, and let's assume we've done that. So here's a situation I'm going to be talking about in this first talk. Imagine you have some code that loads some data, processes it, writes it out, the kind of thing you would do in scientific computing and data science, any sort of data processing. And you try it with a small amount of data, and that works fine. And then you load it with the real data, and your program crashes. And it turns out like you're loading 100 gigabyte of data, you only have 16 gigabyte of RAM, and so clearly that's just not going to work. And so this is the sort of motivation. This is the problem I'll be talking about for the rest of this talk. And so a solution is to deploy a big data cluster. And this is a simple matter of getting a cluster from somewhere, spending a bunch of time setting it up, learning a new API, rewriting your code, debugging a distributed system, which can be very difficult as someone who spent many years working on distributed systems. And to be fair, this is something of an exaggeration. So like today, where there's cloud providers, they have pre-configured systems with a lot of these systems set up for you. So it isn't quite as bad as I'm making it out here. But it does involve often a paradigm shift, a different way of writing your software. You can't just cache things in memory. You have to basically structure everything for this new and different technology in order to scale across multiple computers. And so ideally, you wouldn't have to do this. And so for the rest of the talk, I'm going to focus on how to process large amounts of data with a single computer with a minimal setup, and ideally using the existing APIs, existing code, existing libraries you're already using. The term small big data is due to Alex Voss, Ilya Lvov, and John Lewis. And the idea is that there is a scale of data beyond which you're going to have to use a cluster. Like the people who are doing geoscience simulations, like there's a reason they're using 10,000 CPUs to do those simulations. And there's also, and they really need that many computers, they just have that much data. And there's data that's so small that it's trivial to process it in a single computer. Like if you have a 16 megabyte file, you load it, you do some stuff, you write it out, you're done. But in between those two extremes, there's data that doesn't fit on your computer's memory easily. But with the techniques we'll learn, you can actually process it in a single computer. And that's the sweet spot that we'll be talking about today. And so before talking about the various solutions to this problem, how do you process lots of data if it doesn't fit in memory? One thing to think about is why do you need RAM? Why do you need to store things in memory? Like we have our data presumably stored on disk somewhere. So like my computer has a 500 gigabyte hard drive, solid state drive, in fact, which is faster. So I can store up to 500 gigabytes. So I should be able to process up to 500 gigabytes of data, right? And in some sense, that's true. However, even modern solid-state hard drives, you don't have to physically spin to read or write from different parts of it, are 160 times slower than reading and writing from RAM. And so while in theory, you could just do all of your reading and writing directly to your hard drive, in practice, what would take you usually an hour, let's say, if you're reading and writing from RAM, might take 160 hours if you're reading and writing from a hard drive. So if you want things to be fast, you basically have to fit your data in RAM. Otherwise, it's just going to take far too long. So the first solution, in some ways the easiest, is just throw some money at the problem. These numbers are somewhat out of date. Like computers are a little bit cheaper in theory after a couple of years, but also like we're in the middle of a chip shortage. But you can, when I source this, and I'm sure it's about equivalent, you can get a machine with 6 cores, 64 gigabytes of RAM for $1,000 US dollars, but not a big difference. And I didn't do a lot of price comparisons. You can rent machines. You can get a virtual machine in the cloud with 64 cores, 400 gigabytes of RAM for $3.60 an hour. So if you're going to run a job that's going to take 2 hours and then you're done, you can just spend $8 and a little bit of setup time, just run your program just on a single computer with a huge amount of memory, and you don't even have to optimize anything. You don't have to change your software. You might just be able to load that 100 gigabyte file directly into RAM and just process it really quickly without any changes to your code. So before you get to writing any software, the easy solution is just to think about, like, maybe you can just, if you buy a computer, you'll have it on your desk. You can keep using it. If you rent a computer, it has the opposite benefit of limited costs. But either way, you can just spend more money, get more RAM, and thereby process more data without any changes at all to your code. Does anyone have any questions at this point?
No questions so far. We're good.
Okay. So if you sometimes spending more money is not sufficient or not ideal. So to give an example, at one point I was working on a scientific computing data processing pipeline for a startup. So it was like in the biotech space. And so we were reading this data, processing it, writing it out. And the idea was eventually customers would be paying us to like read in biological samples and do our thing. And some of that money would be spent on cloud computing. And so I did the math. And it turned out that using the amount of time it took to process our data at the time, which wasn't, we were just doing testing at that point, 70% of the company's projected revenue from each customer would have been spent on cloud computing. And so if you're spending 70% of your revenue, you're not making a profit, and there's a decent chance you won't even be able to pay my salary, which, as I was an employee at the time, I thought that was important. So in these sort of situations where you're scaling, so you like, it's not just 2 hours of cloud computing, it's thousands of hours. Or maybe it's just more data than you can process on one computer. You might decide that you want to spend a little bit of time to reduce your costs by restructuring your software to be able to process more data. Excuse me. So there are 3 basic techniques you can use to process large amounts of data in memory. And these are what we're going to be covering in the rest of the talk. You can compress your data, which is to say you can find some way to represent the same information using less bytes. And we'll go into all of these in detail. You can process it in chunks, one at a time. So instead of loading all the data, you can load one small part of the data, and then load a little bit more, and then a little bit more, and a little bit more. And each time only have some of the data in memory at a given time. And then you can index the data, so you only load what you need. And these 3 techniques are really very widespread. So if you've done anything with a relational database, these techniques are inherent to how a relational database works. And so the examples I'm going to be giving for these techniques involve NumPy and Pandas. But pretty much any system you use for processing large amounts of data is going to be using these techniques in one form or another. And so if you're not a NumPy or Pandas user, this is still useful because once you understand these techniques, you know exactly what to look for. You can go to your library and say, oh, how do I compress the data? How do I index the data? And those techniques will work in other contexts as well. The examples I'm going to give are not exhaustive. There are other techniques, even with NumPy and Pandas, you can use to apply compression and chunking and indexing. And so at the end of the talk, you'll get a link to my website where I have a bunch of articles which cover both these techniques and some additional techniques you can use in NumPy and Pandas. Or rather, additional APIs you can use to implement, let's say, compression in the context of Pandas. And finally, there's sort of the generic support that like NumPy and Pandas and whatever your libraries of choice are. But your particular application, the particular structure of your data, might allow you to use specific forms of these 3 basic techniques that only work in your particular situation. And so as someone who is an expert in the particular data that you're processing, you might be able to come up with a specific way to compress your data tied to the particulars of your understanding of which parts of it are important and which parts aren't. And so you might be able to say, oh, I can compress my data by just dropping these parts of the data just aren't important to the results we care about. So the first core technique we're going to be talking about is compression. And the idea with compression is you represent the same data with less memory. And so that can be lossless. And so the compressed data is identical to the original data. Or it can be lossy, which means you're losing some of the details, but you made sure to only lose the details that don't matter. Or maybe you drop or you lose a little bit of detail in a way that's not changes the results a little bit, not in a meaningful way. And so lossy compression, it has to be tied to the specifics of your application. And when I talk about compression, like a common form of compression you're going to see is like a zip file, a tar.gz, or some other way of compressing data on disk. And if you think about it, compressing your data on disk is not actually going to save you any memory. So imagine you have a gigabyte text file, and you store it in a zip file. Now it's 100 megabytes. In order to process it in your software, you're going to have to unzip the file. You may do it on demand, but you're still unzipping the file to get access to the text. And then once you unzip it in memory, you're back to using a gigabyte of memory. And so what I'm talking about here is not the way you compress the data on disk. I'm talking about the way you present things in memory once you've loaded it. And so things like zip and tar.gz are usually not going to help you. You have to think of the next step, what happens once it's actually loaded into your process. And so the first technique I'm going to use an example involves NumPy. And so if you're not familiar with NumPy, NumPy is a library for processing arrays, tensors, large arrays, small arrays, n-dimensional arrays. It's a whole bunch of math operations. And each array has a specific data type or D type. And the D type determines what kind of information you can store in that array. So you can have an array of floats, you can have an array of 16-bit unsigned integers, you can have an array of 64-bit signed integers, you can have an array of 16-bit floats. So depending on what your data type is, you can represent different things in your array and you use different amounts of memory. So for example, a 16-bit unsigned integer can store numbers between 0 and 65,535, or 2 to the power of 16 minus 1. 64-bit unsigned integer can store numbers between 0 and a much larger number, which is 2 to the power of 64 minus 1. So if you want to store large numbers, a 64-bit integer is the only way you're going to do it because it's just not going to fit in 16 bits. However, being able to represent larger numbers comes at a cost. So 64-bit integers use 4 times as much memory as 16-bit integers. And so that means, depending on the range of numbers you're representing in your array, you might end up wasting lots of memory. Let's look at an example. So we're going to create an array just made out of ones. And it's going to be 1024 by 1024, so about 1 million values. And one of the arrays is a 64-bit array. So the D type is UN64. And the second array is UN16, unsigned int, so it's 16-bit. And then we can look at how much memory each of the arrays uses. And you can see that the 64-bit array uses about 8 and a bit megabytes. And the 16-bit, the array of 16-bit integers uses about 2 megabytes, a quarter of this amount of memory. And so if the values you need to store are never bigger than 65,000, if you're only storing numbers between 1 and 1,000, say, using the 64-bit D type is going to use 4 times as much memory with no benefit. And so just by switching the D type, you may get identical results with a quarter of the memory usage. This is a form of lossless compression, presenting the same information with less memory. And you can imagine that you can also use this as a form of, you can also do lossy compression. So for example, if you don't need exact values, you can say, if you're doing financial statements that of large companies, like they're typically going to report them in hundreds of thousands or millions of dollars. You can just not store those extra zeros, and you might be able to fit your data in a 32-bit integer instead of a 64-bit integer or 16-bit integer maybe. And you can just use this memory, and you've lost a little bit of accuracy, but depending on your analysis, it might not matter. Another form of compression is a sparse array, which this is a third-party library, which you can find at this URL. And it's fairly compatible with NumPy. It interoperates, has the same sort of API. So in many, like you can often just, depending on the use case, just swap it out in part of your code. And the idea is, if you have an array that is mostly zeros, you don't necessarily need to waste memory on storing those zeros. And so a sparse array will store only the non-zero data. And depending on the structure of your data, the non-zero data may be distributed in different ways. And so there's different ways you can represent sparse data. And so we're just going to look at one example. And so what we're going to do here is we're going to simulate something that looks like maybe the stars in the sky, or the kind of thing I was doing with scientific data, which was gene sequencing. You have little dots on a very large image. So we have an array, a two-dimensional array, which is 1024 by 1024. And we're going to fill it with random values between 0 and 1. So it's basically just noise. And then what we're going to do is we're going to say any value that's less than 0.9, and we're going to set to 0. So now we have this array where 90% of the values, if you think of it as, say, pixels in an image, 90% of the data is just not there. It's just blank. It's a 0. And then we can use the sparse library to convert the array into a sparse.coo. This is a coordinate representation of the array. And so instead of having 1,000 by 1,000, so 2 to the power of 20 values in contiguous memory, it basically stores these sets of 3 values, like an x coordinate, a y coordinate, and the value at that xy coordinate. So the fewer xy coordinates you have that are non-zero, the less memory it takes. And if it doesn't have an xy coordinate, then the presumption is that that value is 0. And we can look at the memory usage for these two arrays. And for the array that has all approximately 1 million values, it uses 8 megabytes of memory because each of the locations uses 8 bytes. And for the sparse array, it only uses 2.5 megabytes because there's only 10% of the values are actually there. And there's the overhead of storing the xy coordinates, but it's still not enough to, we still save memory because 90% of it is blank, and so we can just omit it altogether. And so the fewer values you have in your array, the better the sparse array does. And the more it fills up, the worse it'll do. And eventually there's a cutoff point where the regular array uses less memory than the sparse array because you've packed in too much information. And you can go to the website and they have documentation, and they may have since added at least one other representation. So that's compression with NumPy. And similarly, you can compress data with Pandas. If you're not familiar with Pandas, Pandas is a data frame library, and you can basically store data that, in columns. Those columns have names and they have types. So it's more or less equivalent to data you'd have in a spreadsheet or a CSV. And the columns in Pandas are typically implemented using NumPy arrays. And so when you load the data, it has to figure out which NumPy D type to use to store the data. So if you load in a CSV, in this case, it's looked at the coordinate column in the CSV, and it'll just guess at a D type. And look at it and say, oh, this looks like numbers. And so the default D type for Pandas when it reads a column is 64-bit. And so it'll use a 64-bit integer for each value. But if you know that the values in that column can fit in a 16-bit integer, when you load the CSV, you can specify for this column, use 16-bit integer as the column D type, and then it will use a quarter of the memory because it's, again, using a NumPy array with a smaller D type there's less memory used per value. And assuming your values can fit into a 16-bit integer, then you just save memory. So are there any questions about compression before I move on?
Yes, there was not a question, but more of a comment, and I think you kind of covered that. About like converting your numbers, let's say from float 64 to float 32. I do have a question though. So you covered different techniques on how you can basically compress your data if you don't need that certain amount of precision. My question is there a more or less automated way or a library that will load your data applying all those compressions without you having to worry about losing like the important information in your data?
I don't know of one. It would be nice if one existed.
Right. Basically, what I mean is, let's say I'm loading a CSV file, and I don't want to apply different compression techniques like the one, for example, you've shown on the previous slide. I just want it to be loaded already with the kind of minimum amount of memory that I can take in my RAM.
Yeah, I don't know of one that exists.
Okay.
Yeah, and I should mention there's a bunch of other compression techniques for pandas. Like you can use categoricals for string. If you have like a limited set of strings, like you can use a categorical, that'll save a lot of memory. But if you go to the link at the end of the talk, you can get more details about that.
Right. Also, on that note, what you're mentioning, so basically if you have a categorical column, let's say in your data frame, and the cardinality of it is fairly small, you essentially can create like a lookup so that it's represented, like you see it still as strings, but kind of behind the scenes, it's represented as numbers and like a dictionary lookup kind of.
Yeah, you might use like 1 byte per value instead of like a minimum of 8 if you're lucky.
Okay. Yeah, that makes sense.
Okay. So next technique is chunking. So the idea of chunking is you often don't actually have to load all of your data to get the answer that you want. So if you think about, for example, getting the maximum of an array of numbers, one thing you can do is load the whole array of numbers. And this is an example, or in this code example, we're assuming you have an array of 100 values, just a demonstration. So if you load the whole array into memory, and then you can just find the maximum. You can also consider that the maximum of the first half, you get the maximum of the first half, the maximum of the second half, then you have 2 maximums, then you do the maximum of those 2, you'll get the same result. So to calculate the maximum, you don't actually have to load all the data. You can load the first 50, and the next 50, the next 50, the next 50, and then get the maximum of each of those chunks, and then you get the overall maximum of all those sub-maximums of subarray. And if you do that, you get the exact same answer, but you haven't had to load all the data into memory at once. And that's the idea behind chunking. So in this example, we didn't, it's a toy, like everything's already in memory, so it's just an example of the way you're thinking. If you're using the NumPy, you need some way to be able to load chunks from disk, ideally as transparently as possible, and then you can run code that loads chunks, processes them, and then unloads them. And a good way to store data in disk is the ZAR format. It's sort of a modern version of HDF5, which is a scientific computing storage format. And so here we're basically opening a ZAR file that has 1 million values in it, and we're saying the chunks are 1,000 long, and it's like 32-bit integers or 4 bytes. And so when you load a ZAR, what you get back is not, if you look here, it's not actually the NumPy array. It's just loading a pointer to these files on disk. So when you open it up, it's not actually loading anything in memory. If you index the ZAR, at that point, it actually loads it into memory and gives you a NumPy array. So only when you index it does it actually load stuff into memory. So to compute the maximum of this array, we can say the maximum is the maximum of loading for each chunk of 1,000. We load it from the ZAR into memory. we calculate the maximum, and then we have a list, and then we do the maximum of that. So instead of having at any time a million values, instead of having at any time a million values in memory, we only have 1,000 values in memory. So it uses much less memory. But we're still getting the same maximum we would get if we loaded the whole thing into memory. And you can likewise use ours to like write out chunks from memory back to disk if you need to persist them. So it's just a nice way to sort of transparently get one chunk at a time of your data. Similarly, with pandas, you might want to process your data one chunk at a time. And so typically when you read a CSV, for example, it loads the whole CSV into memory. You can also pass an argument called chunk size, and it'll only load, in this case, 100 lines at a time. And then you get an iterator that gives you a series of data frames, and it only loads one data frame at a time. So in this case, we're calculating the maximum of a column. And so the maximum is, we start at 0, and then we just, each time the maximum is the maximum of either the current maximum or the maximum of this column in this chunk. And we get the maximum value, and we did it without actually having to load the whole CSV into memory. So any questions about chunking?
Yes, there are a few questions. First of all, will you be sharing slides afterwards?
As I said, like if you go to there'll be a link to a bunch of articles, and they go into much more, like for each of the techniques I'm covering, like I will have like a whole article, or sometimes like an article of that plus 3 other techniques. So I recommend going, and I have one article which is just the overview of the 3 different techniques. And so basically all the information, this talk is there just with more detail, more explanations. So you don't have to like recreate just some slides. So the link at the end will give you all the same information just as prose articles.
Okay. And then another question we have is, and I think you might have covered that with the example of the ZAR library, but the question is, does Python offer a library with APIs similar to Java 8 streams that allows you to load data lazily?
So there's a library, I think, called Streams with a Z. Something like that.
What is it spelled?
STREAMZ.
Oh. Okay.
Yeah. And there's probably at least a couple of the libraries. And I guess one thing I should add is there's the Dask library, DASK. The Dask library is designed for parallel computing, but you can also just use it on a single machine or even on a single CPU. And in order to do parallel computing, if you think about it, you want to be processing chunks in parallel, you have to chunk your code up. And so Dask re-implements the NumPy, large parts of the NumPy and Pandas APIs, and then does chunking transparently behind the scenes. And so instead of having to do chunking manually, you can use Dask, and it'll just do the chunking for you. And it's actually quite simple to set it up as a library. Like it's not, you can scale to like thousands of machines, but you can use it on one computer trivially. And so it's a really, if you know chunking is the way you're going to go, you might want to consider Dask as a way to process the data, because it'll just do the chunking just transparently for you.
Okay.
And there's an article about that on my site.
Yeah.
So the third thing.
Sorry, there's a few questions actually, so they kind of accumulated quickly. So the next question is, would using ZAR increase the access time substantially?
So ZAR, like you're reading from disk, and so that will slow things down. However, you read from large chunks, and so that like sort of amortizes it. ZAR can also use compression, so you're doing less reading from disk at the cost level of CPU usage. And so yes, the idea is if you're dealing with data that just doesn't fit in memory, the alternative is that you wouldn't be able to process it at all. And for expensive computations, the cost of reading it for disk probably won't matter once you're dealing with enough data. So the idea is like, if you have enough data that fits in memory, you don't need to use R at all. You can just load the data. You don't have to do any of these techniques. Just load the data, process it, you're done. Like if you can use compression and then like everything fits in memory, then you're done. And you don't have to think about like, how do I deal with data that I can't load? But if you do, then you don't have a choice. And so ZAR is a good way to do it. And the compression means you do less disk reading, writing than you would otherwise.
Okay, thank you. Yeah, we're good for now.
Yeah, and it's extremely hot. And I unfortunately closed room and I forgot to get some water. So I'm just going to ask someone.
Okay, we can take a pause right now.
Well, I'll just see if I can ask someone to get me some because
all right.
I did not expect it to be this hot in here.
That happens.
But it's like, yeah, 90. It's in the 90s.
And we'll just keep the slide on and remove everyone from the stream for a moment.
3 seconds. Sorry, I did not.
Yeah, and we are
realize
back.
how hot it gets in here when I don't have access to air conditioning. So third technique is indexing. And so the idea with indexing is that an index is a summary of the data. And so that comes from like an index of a book. So imagine you're reading a book about animals and you want to learn about pandas. And so one thing you can do is just read the whole book, beginning to end, and just eventually you'll hit information about pandas. Or you could read the index at the back of the book and it'll tell you that pandas are at pages 260 to 275, and there's another bit at page 350. And you can only read those parts of the book. And if you only have to read those parts of the book, you only have to load that into memory. And so the index lets you more efficiently figure out what data to load into memory and only load that data. And the index, because it's a sort of just a map, a summary of the data. So for example, the index in the book or the table of contents at the beginning of a book, they're both much, much shorter than the book itself. They're not the data, they're just pointers to data. So you can easily fit the index in memory, or at least you won't have to load it as much from disk, and then you can use the index to only load the data that you actually care about. And so if you think about indexing and chunking, in both cases, you're loading part of the data from disk into memory at a time. So what's the difference? The idea with chunking is that you need to load all of the data in order to answer your question. But you can get the answer you need only by loading one chunk at a time. So if you're answering the question is, what is the longest word in this book? You're going to have to load all of the data. You can't answer that without looking at all the data. But you can just load, let's say, one page at a time from the book, and that will give you the answer. On the other hand, sometimes you'll need a subset of the data, and that's when you would use indexing. For example, if the question is, how much data did the company spend in, how much money did the company spend in July? You don't care about June, you don't care about August, you don't care about September, you don't care about last year, you only need July. And so you only have to load some of the data. And so chunking is when you need to load all the data, but you don't have to load it all at once. And indexing is when you only care about some of the data. And quite often, you'll use both of those techniques together. For example, let's say you want to know how much money was spent in July, and it's a really large company. You may still not be able to load all the data into memory at once. And so first you'll find all the data for July, and then you'll process it in chunks. And so you can use both techniques together. And the simplest solution for indexing is just to store all the data in a single file per month, let's say. So if you want July's data, you load the CSV for July. And for certain kinds of data, this is like trivial to implement, and then a really simple way to just load the data, only the data you care about. But sometimes you need to go a bit further, and so we'll do that with pandas. And so we'll start with what the code looks like if you're not using indexing. And so let's say you are doing campaigning for a political campaign, and so you're sending out people to knock on doors, and each volunteer is going to be knocking on people on a specific street. So you have a voter registration database, and you want to know who lives in a particular street. And so what you can do is you can use read the CSV in chunks, and then for each data frame, filter down by the particular street name. And so find me all the people who live on Main Street. And then you have like a bunch of these little tiny filter data frames, and you concatenate them into one big data frame. And you get the result. And so we're loading only a subset of the data. We're loading only the voters who live in a particular street. And we're doing it with chunking. And so in some sense, this is fine, right? You don't need indexing. You could just do everything with chunking. The problem is that each time we do this, we are going through all of the data we have. And so if you have a city with millions of people, this starts adding up, right? Because you have to go through all millions of people to figure out who lives in a particular street. That can start getting slow. So instead, we can use indexing. And one easy way to do indexing is to store your data in a relational database, because they have indexes as a built-in feature. And SQLite is really nice relational database. It's actually embedded into Python. It stores it. There's no server. It's just a library. It stores the data in a file. So it's really easy to use. It makes things much easier. So what we're going to do is we're going to do like an initial pass where we just store the data into the database. We'll move it from a CSV into a SQLite database. So again, we read things in chunks, and then we use a handy pandas command to just insert it into a voters table inside the database. We append new rows. So pandas makes it really easy to shove the data into the database. You don't have to think about column names or tables. You just 2 lines of code and you store it into the database. And then we do this handy command where we're saying, hey, database, I'm going to be searching by street. So please create an index. And later, when I search by street, you can, instead of having to scan every single row in the database, SQLite will know that it can use the index to only load the rows that are relevant. So we run this program, and we do it once. Now, all of our data, the exact same data is stored in a different file, voters at SQLite. It's the exact same data, but easily accessible from a database, and more importantly, with an index. And so now we can rewrite our query function, loading voters for a particular street. We open a connection to the database, which again, this is just a library. There's no database server. It's just a library you're importing. So we open the database file. We have a query, which is select all columns from the voters table where the street equals some particular value, which got passed in. And then we use a pandas function to take that SQL query and turn it into a data frame. So from the perspective of whoever's calling this function, they don't know that it's in database. All they know is they get back a pandas data frame of the voters who live in a particular street. But SQLite is using the index to only load the data it cares about. And so we would expect that it'll be able to do so much faster. Let's compare the 2 different versions we had, like the SQLite version that uses indexing and just the chunking version that uses the CSV. I'm using the voters for the city I live in, not that big, 70,000 voters. So if you think about the memory usage, in the chunking version, every time we load 1,000 rows at a time, and we accumulate whatever memory we need for the result. In the indexing version, the memory usage is whatever the size of the index is, which is tied to the number of streets, which is much less than 70,000, and then whatever memory is for the result. So both of these techniques have reduced the memory usage significantly. if you look at the time to run these queries, the chunking version used almost 60 times as much time as the indexing version. And so indexing has the benefit of reducing the memory usage, but it also does so in a way that if you only have to load subset of the data, it can speed up your query a lot too. So it benefits you both ways. So are there any questions about indexing?
No, not from the audience, but let's say for the previous like few slides where you showed that you can create an index on the street column. What if for like hypothetical example, we wanted to like create indices on all the columns of our data set? What are the downsides in this case?
It would use a little bit more disk on space, and when you loaded it, it may or may not use a little bit more memory. But again, the indexes are much smaller than the actual data. And so there aren't necessarily that much downsides. It might,
Okay.
it might just
All right. Yeah,
make
makes
queries,
sense.
like it will allow you to do arbitrary queries faster. I mean, once you hit like you have 200 gigabytes of data, then you might want to talk to someone who you need to start thinking about how you want to structure indexes in terms of size and disk access and so on. Like you need maybe a more significant database that for simple queries like SQLite will actually scale really well, and it's really easy to use, and you can just create a few indexes and everything will work nice and fast.
Okay, we actually have one more question just appeared from the audience. In the previous example, so that meant the last slide that you were showing with the timing. How long does it take to create an index, and is it included in the 10 milliseconds that you were
showing? Good point, yes. So I don't remember how much long it takes to take the index. It would take at least 500. It would probably take a few seconds. And so if you are only loading the data once, there's no point in using an index because you have to do the chunking to populate the database. You have to do the chunking. So if you're only doing this query once, then there's no point in using indexing. Just use chunking and you're done. The indexing is useful when you're doing multiple queries against the same data. So today, today I'm loading these 10 streets. Tomorrow I'm loading those 10 streets. Today I want July's data. Tomorrow I want August's data. So in those situations, the one-time cost of the indexing is worth the huge speed up of the lots of queries. But if you're only doing the processing data once, yeah, indexing isn't going to give you much.
Right. There was a related question. How long does it take to create the SQL table itself? But I'm guessing the answer to it is the same as
in this case, loading the data, the chunking took about 600 milliseconds. I would expect creating the SQL database to take twice that. Like it'll be on the order of SQLite's fast. So it'll take 2 seconds, 3 seconds. Like SQLite it's not a toy. It's actually quite optimized. It's not written in Python. It's written in C. It is one of the most deployed pieces of software on the planet. But it's a really impressive piece of engineering. It's really fast and very high performance. So there's overhead from Python, but it's not a toy, and it's just tiny, but it's not a toy. And so your computer's not going to grind to a halt. I would expect for this data, it would only be a few seconds.
Yeah, I think a lot of people don't quite realize that a lot of the desktop applications, mobile applications, they actually run SQLite without them realizing it.
Yeah, and it's millions of embedded devices, and if you're interested in engineering at scale and reliable engineering, they have a lot of interesting articles on their website about how they design SQLite.
Okay, we're good with questions for now.
Okay, so we've been giving lots of examples from Pandas and NumPy, and you might be using other libraries or other tools. But the underlying root causes for that necessitate these techniques are still there. Like memory is fast, but it's expensive. Like on my computer, memory is often at capacity, but like so if you think about CPU, your CPU is often just sitting there idle, but your memory is often full. And disk is cheap, like I have way more disk than memory, but it's much slower than memory. And so you need some way to bridge that gap between the cheap storage and the fast but smaller storage. And the same basic strategies, compression, chunking, and indexing apply. Streaming is either just another name for chunking, or in other cases, it's chunking where you have an infinite stream of chunks. But it's sort of basically the same sort of category thing. And so if you know about these techniques, compression, chunking, indexing, you know what functionality to look for in whatever library you're using that processes data. Whatever you're using, they're going to have some way to do these things because they're so basic. It's the way people process data. Like these techniques are like how the databases that have been built up over the past 60 years work, 70 years. And so all of these techniques will be possible in some way or another with whatever libraries and technologies you're using. Don't forget about just throwing money at the problem. Sometimes the easiest thing to do is just to buy more RAM for your computer or rent a virtual machine. And then you don't have to change your software at all. And again, if you want to learn, go over all these details, if you go to pythonspeed.com/memory, everything in these slides is there with in much more detail. I guess I can actually show you. There's when your data doesn't fit in memory, the basic techniques. So that sort of goes over at the high level, and then there's a bunch of articles about pandas, articles at NumPy, and they go into just about Python code in general. And so it goes into much more detail about how to structure your code and other techniques you can use for compression and chunking and so on. And I've also actually written an open source memory profiler for data science and scientific computing called FIL, F-I-L. And it gives you the peak memory usage of your process, which is the thing you want to optimize. Most memory profilers are designed for web servers, which have different sort of requirements. And so if you're trying to measure your memory usage and figure out if you're doing better or doing worse, where you're wasting memory, I highly recommend checking it out. It's open source, runs in Linux and macOS. And that is the first talk. Any more questions?
No, we don't have any questions right now. So what I'm suggesting is we take like a short 3-minute break before the second talk. And yeah, so let me start a timer and share it. All right, so I'll remove everyone from the stream right now, and we'll be back in 3 minutes. All right, and we are back and ready for the second presentation.
Okay. So today's second talk is about a best practices process for Docker packaging. And again, on my website, there's lots of articles about Docker packaging for production. And I'll link to them and a prose version of this talk at the end. And okay, so Docker packaging is complicated. And there are a number of reasons. And so one reason is history. So Docker builds on literally 50 years of technological decisions, going back to Unix in the 1970s. So like Unix signals, the way they work, actually interact with Docker packaging in an annoying way. And that technology is like from 1973, I think. And there's networking in the 80s, Python, Docker in the 10s. Don't really want to talk about the 2020s so far. And so 50 years of technology, like all these different things intersecting in one place. And so the result is there's a lot of details you have to get right when you're doing Docker packaging. And then at the same time, packaging your software with Docker is at the intersection of a whole bunch of organizational processes. So writing the software, testing the software, deploying it, the way it runs when it's in production, what happens when it crashes, how bugs get reported back to developers. And so because it has to interact with all these processes, that adds another layer of complexity. And so there's just both of these things at once in the same place. And just it means Docker and more broadly software packaging is just a very complicated domain. And so because there's so many details in like a half an hour or whatever talk, I can't actually cover all those details. Like for Python in production specifically, I've been collecting best practices. I'm up to about 70, might be more like 80 at this point. I teach this training. It takes a day and a half at least for some of them. Like I can't go over them in this little time. So in order to learn something useful, I like to cover sort of a big picture approach. If you are taking your software and packaging it for Docker, so you have a machine learning job and you're going to run it in one of the machine learning workflows that run on containerized systems, maybe it's a web application. Doing the packaging before you run in production is just one task among many, and it's often going to be lower priority because the point is to run the software, not to package it. And so you might get interrupted. You might get called away. There's an emergency, and then you don't finish it. Because of this complexity, it's very easy to get distracted or not know what to work on first. And then so you spend a bunch of time making your image nice and small, and then you don't think about security. And then you get interrupted and you have to deploy your software, and you have a nice small image, but it's an insecure image. That's not a good trade-off. So today we'll be covering a process for Dockerizing your software that is iterative. So each stage builds on the previous stage. So if you're interrupted, you're at a decent stopping point. Most important parts are first. So if you run out of time, at least you've done security. May not be the smallest image, but at least it'll be a secure image. Again, each step builds on the previous step. And having this sort of process, this big picture set of priorities, can help you think about what are the specific tasks you have to do at each point, what's important, what's not, and think about packaging more holistically, and not just about not getting lost in the details and actually thinking through why you're doing it and what's important. And this is sort of the big picture process that I recommend, which is start with getting something working, make it secure, get it running in an automated way in CI, like have a build system, make it more correct and debuggable, and make your builds reproducible, and then work on optimizations like faster builds and smaller images. And this order is sort of generic and doesn't apply for everyone. So in some applications like reproducibility is one of the first things you're going to do. But this is sort of a starting point, and at least having this framework lets you think about what your priorities are in your particular case. And then the rest of this talk will be structured using these 6 steps. And so the first step is to just get something working. If you don't have a working Docker image for your application, then it doesn't matter that it's secure or automated build, reproducible, or whatever. Like if it's not running, then what's the point? And so this is a really simple Docker file where you said, use this base image, copy in my source code, install it, and then when you run the Docker image, here's how you run it, and that's it. And this is not the best Docker image. There's some security things that are missing. When you rebuild it, it'll rebuild slower than it needs to. It might be larger than it needs to be. But if it runs your application, you're already better off than you were before you started. And then in the future steps, you can improve things iteratively and get a more secure image, a more reproducible image, and so on. So any questions about the first step?
No, we're good.
Okay, so now you have this image, it runs your application. And so before you can deploy it anywhere, before you can even run your software publicly at all, you want it to be secure. If it's not secure, then you're going to worry about deploying it, or if you do deploy it, someone might take it over. And so the next step is to take your image and take some basic steps that'll make it a little bit more secure than otherwise. So here's an example. By default, Docker images will run as a root user. And a container is a much more locked down environment than just running a normal process. So root inside a container isn't quite as bad as root outside a container. But root inside the container is still a bigger attack surface. And so if someone were to take over your container somewhat, if they have root, then it'll be easier for them to escape the container and take over the whole machine. And so it's a good best practice not to run your container as root. And so in this image, we've added a few more commands. You run a command to add a new Unix user, and then we use a Docker command to change that user, and then we set the working directory to its home directory, and then we install the code in that user directory. And so now when you run this image, instead of running as root, it'll run as user app user. And so it'll just inherently, if someone takes over the container, it'll be harder for them to escape from the container because it's more locked down. Beyond the sort of configuration details for, don't want to run as root, you also want to be thinking about the processes involved with packaging. So a Docker image is an immutable artifact. So once you've created it, you don't change it anymore. The whole point of a Docker image is that it doesn't change. And so if you have a security update, you're going to have to generate a new image. And so if you think about what that means about rolling out security updates, you need some way to learn that security updates are necessary. And then you have to update your image. And then you might need to change your Docker file or change your list of Python packages you're installing. If there's a security problem in a Python package, you have to rebuild the image. And then if it's a server, you have to redeploy. And so this process of rolling out security updates isn't about editing your Docker file or editing a Python script. It's an organizational process, right? It's something that needs to be done to some extent by humans, or at least that humans have to design, even if it's automated, right? And it's not just about editing a few config files. And so security isn't just about your configuration, it's also about putting these processes in place. And so that's just two of the examples of things you want to do to make your Docker image more secure, and there are others. So any questions about security?
Yes. So one question we have, do you have any guidelines, tips to share data via mounted volumes when Docker user ID is not the same as the host user ID.
Yeah, so if you're I can share a link to an article at the end, but if you think about, just to emphasize the perspective here, what I'm most of my of this talk is focusing on running Docker images in production, and production has, like, you're running your website or you're doing machine learning jobs that are running in an automated manner. Anything that you're running locally, you don't have to, like, it's a sort of fundamentally different mindset, because it's just another piece of software you're running locally in your machine. So you don't have to worry about, like, you don't, all of these worries, these things don't matter as much if it's just like a piece of software you're running just in your own machine. And so you don't have to spend much time about thinking about packaging. You can just do the easy thing, and you can skip most of these details. That's just the thing I want to emphasize. But in terms of matching, so if you're trying to match your local file system user IDs, probably security is not your main concern. When you start up when you create a Docker image, you can set a default user, but when you run it, you can also override that with a specific UID. And so you can run your Docker image in a way that matches the user ID of your local file system. This should only be an issue in Linux, I believe, on macOS, and almost certainly Windows. This happens automatically, and you don't have to think about it. I'll give a link at the end to an article that talks about that.
Okay, then we're good.
Okay, so far we've made the image work just at all. We've made it secure so we can run it publicly somewhere. And up to this point, the presumption is you've been building these Docker images manually and then like maybe deploying them to a test server. But next you want to automate things so that you don't have to manually do a build. You might have teammates who also want to build images. You might want to like run automated tests using your images. You might want to automatically deploy. Every time someone merges the version control, you might redeploy your new version of your machine learning workflow or your web server. So the next step, the third step, is to do automated builds, integrate with your build or continuous integration system. And so it might be as simple as like this little tiny script here, which basically runs your tests, builds your image, and then pushes it to an image registry where you store your Docker image. But it might be a much more sophisticated setup that like runs integration tests using image or deploys things automatically every time a new image is built. And again, it's not enough just thinking about configuration files. You also have to think about how building Docker images integrates with your development processes. So for example, how are tests going to work? Do you run your tests before you create the Docker image? Do you run them inside the Docker image? Do you use the Docker image for some sort of integration testing? How are you going to deal with branches? We'll give an example of that next. You have two developers working on different branches. Like, do they both want Docker images? Are you sure that their Docker images won't like stomp on each other? If Docker packaging is part of your build system, is a slow Docker image build going to be a bottleneck for developers? Like, so you have to wait 20 minutes for the Docker image to build. And so you need to think not just about configuring your files, but also like how your packaging integrates with the way you're doing software development. To give a concrete example, it is pretty common in software projects to do branch-based development. So let's say I'm working on feature number 123, more cowbell. So I'll create a branch called 123 more cowbell, and I will do all my work on that branch. Then eventually I'll do a pull request, and some tests will run. That'll get merged in, and if it gets approved, the pull request will get merged into the main branch. And so it may be that in addition to building Docker images off the main branch, which are the ones that run in production, I'd like to build a Docker image from 123 more cowbell automatically when I do a pull request, maybe for some integration testing. And if you do that, you don't want the in-development code to create a Docker image that stomps over the production Docker image. Like, you don't want the random half-broken code in my branch, create a Docker image, then replaces the production Docker image. So when you build your images, you might want to give Docker images different names depending which branch they came from. So in this example code, I'm using this handy git command, which I got from Stack Overflow, to figure out which branch the code is on. And then when I build the image, I name it your image : branch name. And when I push it, it gets pushed with a name, your image : branch name. So that way the Docker image for 1, 2, 3 more cowbell will have a distinct name from the Docker image for the main branch, or the testing branch, or what have you. And so the idea is that you can get Docker images, but from different branches, and they won't stomp at each other. And that way, you can sort of integrate Docker images into your branch-based development. And again, this is just an example. There's a whole bunch more best practices you might want to do as part of your automated builds. Are there any questions about this step?
No question from the audience, but I do have like a question that I don't know, maybe it's better suited for the end of the presentation, but I'll ask it now. So you were talking about best practices, but maybe at the end you can also mention some of the common mistakes or maybe anti-patterns that you see companies and people do with Docker without like even realizing it.
Yep, I can do that. So the next step is operational correctness and debuggability. And the idea is at this point, you're doing automated builds, your teammates are doing automated builds, so now you have a whole bunch of Docker images, maybe they're even running in production, and you want it to run well in production. Like, so saying crashes, you want good error messages. If someone tells you, I got this bug on this version, you want to know exactly which version of the Docker image it is and how it maps to the particular versions of the code. So you want to be able to map between specific images and specific versions of code. You basically want things to just work more smoothly and be able to understand things better now that it's actually running in production. And so I'll give a couple examples of ways you can do that. And so one is logging. Now, so you're running your code in production. Sooner or later, something will go wrong and you get a bug. So a bug in Python code that breaks things enough, you'll get a traceback. So like you'll get a 0 division error. Some number unexpectedly 0. The 0 division error will end up in your logs. And so when someone files a bug, you can look at the logs and say, oh, this line of code in this function called this line of code in this function, and gave me the divide by 0 error. And so already you have some sense of where the problem is coming from, what you need to do to debug it. If you have a bug in C code, a common way for this to manifest is your program crashes silently. And so all you know is that your code, your server, or your machine learning process, whatever, just crashed. You don't know which library caused it. You don't know what line of code. You've got nothing in the logs. It's just silent. And C, there's just a lot of C code in like real Python projects, like all like NumPys and Pandas are using C code, like the Python interpreter itself has written C code, all those machine learning libraries, database adapters to talk to Postgres. Like these things happen. And so you want to be able to figure out which library, which function, like what caused it. So Python has a really neat feature called fault handler. It's built into Python. And if you just set this environment variable in your Docker image or on your computer, just anywhere in your automated build system, if you set the Python fault handler environment variable, then anytime your Python program crashes with a seg fault or what have you, you'll get a Python traceback saying it crashed in this function called this line, just the same sort of traceback you get from normal Python code. And this is hugely valuable in debugging crashes because you can say, oh, it's a bug in matplotlib, or oh, I passed the wrong argument to this Postgres library, like as opposed to just it crashed. So just adding this one line to your Docker file or your build system, and you'll get much better logs if you have a C crash. Another example, this is the place where like different applications have different requirements. In some applications, you start up a thing and it runs for like 10 hours, like it's a data processing pipeline. You don't care about the startup time at all. In other cases, like you're doing something like AWS Lambda, like a serverless, where it might be each time you're handling a command, you're actually starting Python from scratch. And so the longer it takes Python to start up, the longer it'll take to process requests. And so you want Python to start up as quickly as possible. When Python starts up, it loads in the .py files, and it sort of turns them into bytecode files, PYC files. And it's just faster for it to load PYC files. So next time around, it can load the PYC file and then start up faster. The problem with the Docker image is that Docker is immutable. So each time you're starting with the exact same file system as before. So if you don't have a PYC file in your Docker image, you will never have a PYC file in your Docker image. And so startup will be slower. And so when you build your Docker image, you can run these two commands to precompile all the code in your Python code to bytecode files, and that will give you slightly faster startup. And again, in some cases, this is a waste of time because your Python program starts once, then runs for 10 hours, and those extra 50 milliseconds are irrelevant. In other cases, those 50 milliseconds in startup matter. And so this is an example where best practices are a thing, but they tend to be situational, and so you do have to apply some judgment about when and where to use them. Any questions about this part? And again, there's lots more best practices for this.
Yeah. No, we're good for now.
Okay. So at this point, you've got your program running. It's secure. And so far as your packaging can make it secure, it's automated builds. Like everything's running smoothly. You have nice debugging information. And so if you think about the lifetime of software, like you're building your Docker image, took a few days, maybe got interrupted, maybe took a couple of weeks. All the libraries you depend on probably haven't had any major releases. Like Pandas doesn't release that often. If you're doing a web application, Django doesn't release that often. So nothing's much changed. 6 months have passed, there's going to be another release of Pandas. 2 years, there's going to be new releases of most of the libraries you depend on, and some of them are going to be incompatible or have changed in a bunch of ways that you need to address in your software. And so you need to have some processes in place to deal with the fact the software you depend on changes. And the basic idea is you want to sort of balance. On the one hand, you don't want things to change without not under your control because your software will break. On the other hand, if you never change anything, if you never upgrade any software, then you're going to have problems with security updates. You're going to have problems with the fact that you're using a 2-year-old library and now it's not getting updates. And so its reproducibility is not just about freezing things, it's also about the processes you use to update your software. Unless it's like a one-time scientific analysis where your only goal is to say, I want to run this exact same thing for the next 20 years. You need some processes in place to update. And so one example of ways you can get reproducibility is by choosing a good base image. So when you create a Docker image, you're using some other image as the basis. And typically it'll be some Linux distribution. And so you want one that will guarantee stability while still giving you security updates. So it won't change the software, it'll just give you critical bug fixes and security fixes. So like Ubuntu long-term support, Debian stable, CentOS, although CentOS is going away, there's replacements, Red Hat Enterprise Linux. All of these Linux distributions guarantee that for the next 3 or 5 years, sometimes longer, they will be backwards compatible as much as they can, but they will still give you bug fixes. The sort of official Python Docker images, so like the ones that are just Python, are based on Debian stable with an add-on of newer versions of Python you'll find in Debian stable. So it's like a good combination of a stable operating system and updated versions of Python. And so if you use this as your Python base image, it says, give me the latest .release of Python 3.9. So that's not as reproducible as you might want. If you really want exact ones, you can do like Python 3.9.2. Slim means a slightly smaller version, and Buster means Debian Buster, which is like the 10th release of the Debian Linux distribution. Debian names their releases after characters from Toy Story. And so each release is named after a different Toy Story character. So partly reproducibility is about things like having a good base image, but it's also the process. And you can think of two extremes. And one extreme is every time you rebuild your Docker image, you get the latest version of all your Python dependencies. So you get the latest version of Pandas, get the latest version of Flask, and if you do that, you'll always get the latest security fixes and features, but also your software will probably break at random. So like you'll go and do like a tiny bug fix in your business logic and rebuild your Docker image, and now it's using like 3 new libraries, and now your code broke, and you don't know if it's you don't know if it's your dependencies. It's not reproducible. That's not great. And so what you want to do is you want to pin or freeze all your Python dependencies. And there are various tools to do that. There's pip tools, poetry, and pipenv if you're using a pip tool chain. There's a tool called condalock if you're using conda. And all these tools basically allow you to take your dependencies and get a frozen list of exact versions of everything. And then every time you reinstall or every time you build a Docker image, you'll get exact same libraries. And it'll be exactly reproducible. That on its own, however, is not enough, because once you've locked your dependencies, you also need some process in place to update them. If you don't, then you get into a situation after 2 years, you really need to upgrade, but you're upgrading 10 major things at once, and then it's really hard to make things work. And so in addition to freezing your dependencies for your Docker image, you also need some sort of ongoing organizational process where every 3 months, or let's say, even regardless of security updates, you go and update your dependencies so that you're never that out to date. So you're basically stable for 3 months, and then you have time in your schedule to update every 3 months. Because it's every 3 months, none of the changes are too big. And so you're both using the latest version of everything while still preserving stability and reproducibility. So any questions about that?
No questions. We're good.
Yeah, and again, because this is an overview of the process, I'm not going into the details of how to do these things mostly, but there's a whole bunch of articles on my website that talk about like how to do reproducible packaging for conda and how to do it for pip and so on. And so now that your build is reproducible, your Docker image is basically done. Like it's everything is correct and hopefully and working and automated, and the only thing left to do is to optimize it, to build things faster, to make your images smaller. And faster builds and smaller images will like make sure you and your team aren't wasting time waiting for builds. Things will download faster. Like it's not necessary, but it can save you a bunch of time and money. And so it is often worth doing. And like, for example, for data science Docker images, it's very easy to get an image. It's like 3 gigabytes because all the Python packages for machine learning are all gigantic. And so like even tiny tweaks can make a big difference in image size, for example. So here's an example of a way to get slow images, if you're talking about bad practices. In many places, you will see a recommendation to use Alpine Linux as the base image for your Docker image because it'll give you smaller images. And if you're a Go programmer, that's fine advice. As a Python programmer, though, this will result in extremely slow builds. And the problem is that typically when you do like a pip install of pandas, there's a bunch of compiled code. But people who maintain pandas upload precompiled versions for Linux and so on to the PyPI package repository. And so you do pip install pandas, it's downloading a precompiled version. You don't have to compile anything. However, because of the way Alpine Linux works, it can't use wheels, precompiled wheels. And so you have to compile everything from scratch. So for example, if you install pandas in Matplotlib, if you install them on like a standard Linux distribution like Debian, so this is a Debian-based image, like same for Ubuntu or Red Hat Enterprise Linux, it'll take you 30 seconds. Just download and install precompiled binaries. It's mostly tied to how much bandwidth you have. If you install with Alpine, it'll take you 1,500 seconds because you have to download and compile lots and lots of C code. And you have to figure out which C libraries to install and which headers, and it's just a pain. And so there's some work. There's a Python enhancement proposal about getting binary wheels for Alpine Linux. And so in the future, this problem might be fixed, and you can use Alpine Linux and get fast installs. This is a process. It's not going to happen for another, like most libraries are not going to have this for a while. So if you care about how fast your builds are, just don't use Alpine Linux. So just to recap, I guess, any questions about optimization?
No questions.
Okay. So to recap, process is first get something working, make it secure so you can deploy it publicly, automate the build so you're not doing it manually, make it run well, make it reproducible, and then optimize it for faster builds and smaller images. And this is both in order to do and also just when you think about how to do things, figure out what your priorities are. In some cases, reproducibility is like even more important than like automation. In other cases, like you don't care about image size. But this order is sort of a good starting point to think about packaging. And I want to emphasize something that I brought up along the way, but it's just worth repeating. Packaging your software isn't just about like creating some configuration files like a Docker file and so on. Packaging in general and packaging for Docker specifically is something that interacts with your development processes and the way version control works in your organization and testing and continuous integration. And it requires you to set up ongoing processes. If you're running software in production, you have to think about security updates. You have to think about how you're going to learn about security updates, how you're going to make sure they get rolled out. And you also need to think about things like dependency updates, like how are you going to deal with the fact that Pandas or Flask or whatever are continuously having new releases? How do you make sure you both have reproducible, stable builds, but also your software doesn't get stuck up being out of date? With like the most extreme case being software project is still running on Python 2, even though at this point it's been deprecated for a year and a half. So packaging isn't just about creating some configuration files. It's about setting up organizational processes you need to actually run software in production over time. So that's the end of my talk. There's a prose version of my talk at this URL. Of this talk at this URL. It's like a 10-page article, goes into sort of even more big picture view of like why you should organize things this way and how to think about packaging. And also I have this URL, pythonspeed.com/docker. Lots and lots and lots and lots and lots and lots and lots of articles about all of these best practices, or most of them at least. Not all 80, but a lot of them, or 70, but a lot of them. And so if, for example, you're like, how do I get reproducible builds for Conda? There's an article about Conda lock and explaining the sort of why you need it and the two kinds of configuration files you need and so on. So there's a lot of articles in there about Docker packaging. So if you're interested in particular details of Docker packaging, it's pythonspeed.com/docker.
Right. Yeah, I do have one question. So what's your view on what I frequently see in many Docker images is running apt-get update?
Yep. So this is so if you are using a stable base operating system, so Debian stable, Ubuntu long-term support, CentOS, although CentOS will stop being stable any day now, but Red Hat Enterprise Linux. If you're using one of these Linux distributions, which you should be, then you make sure that you're using a particular version of the stable base image. So you're saying, I want Ubuntu long-term support 2004. Right? So you don't like switch from 2004 to 2204 in April 2022 by mistake. Like you have a base image that's a specific long-term support version. Then when you do apt-get upgrade, to install upgraded software packages, what you're getting is just security updates and critical bug fixes. Like the point of a long-term support stable-based Linux is that they're guaranteeing you that everything will be compatible on the level of like C library binary interface in terms of features, and they will do their best to only backport critical bug fixes and security bug fixes. So you do want security fixes in your deployed software. You do want critical bug fixes in your software. Like you don't want it if there's like some data that bug that corrupts data and like some library you're using, you want that bug fix. And so it is actually a important thing to do is to run that in order to get security updates. There is an alternative approach you can take where you say, instead of saying upgrade everything, you say, I want this particular version of each of the, say, Debian packages. I want glibc 2.32.6-5, the exact package name. And then you do that for all the packages. And that way you have exact control of everything if you really want it reproducible. And if you do that, you need to actually make sure you have a process in place to update those. Otherwise, you won't get the security bug fixes. You won't get the critical bug fixes. But if you do it this way, then you'll get, you'll have a little bit more stability. Although in practice, it's rarely the source of incompatible bug fixes. Python code is a much more likely source of instability. Like because the operating system is, because like Ubuntu long-term support, like they have people whose job it is to make sure that it's compatible. Whereas, so like if you get the latest version, it should only be bug fixes. Whereas if you get the latest version of Django or the latest version of Pandas, like it may be quite different from the latest version of Pandas or Django 6 months ago.
Okay, yeah, makes sense. So yeah, I don't think we have any other questions. So thank you very much, Itamar, for taking the time and present. Like I'm sure our audience, like I myself, learned quite a few things today, and we'll definitely check out your blog. So thank you very much.
Yeah, sorry for getting dehydrated halfway through. And yeah, if you go to pythonspeed.com, there's everything I talked about is there with more details and much more.
Okay, perfect. Again, thanks to Itamar, and thanks everyone who attended today. And enjoy the rest of your evening. Bye, everyone.
Thank you. Bye.
Bye.